The Automotive Pilot of ASSIST-IoT is covering the future of the transport fleets. We are considering growing fleets where there is a huge variety of vehicles of different models, and also we can have different variants, regional variants, and different sensor sets. And at the same time, we want to have a very improved monitoring capability for being able to track the emission profile of each one of the vehicles in the ever-varying use cases, and also advanced diagnostics characteristics in a way that we are able to deploy advanced diagnostic methods and just to fit models and these methods just on demand. With the diagnostics methods on demand, we are just able to deploy advanced diagnostic methods in the different vehicles. So whenever a vehicle is suspected to be faulty, we can deploy software components that are centered in diagnostics different sensors. If we detect a fault, we can then send the service to service, and once in technical inspection, the service technician can get direct instructions on the faulty element and how to fix that.
The ASSIST-IoT architecture has different properties that have been very useful in this business scenario, which requires scalability, mobility, and distributed processing. The project also provides a set of enablers that can be used to tackle the use cases explained before. First, thanks to the project's smart orchestrator and the manageability dashboards, we can manage not only a car, but large fleets of them, which act as edge computing nodes. This means that we can deploy common services or applications on top of them, individually per car or in a group of them. And then we can also monitor them and retrieve data from them. With respect to data, the pilot makes use of the Edge Data Broker, a data distribution solution based on MQTT with extended capabilities to move raw or processed data at the cars to the cloud. There, it is stored in a long-term storage enabler, where it can be consulted and later on visualized with the business KPI enabler. The service in charge of gathering and processing the data at the cars can be changed over the air, in case that the automotive company wants to retrieve other kinds of data or update it. These mechanisms are also used to notify the cars when new calibrations for their control units are available, so they can retrieve them from an exposed semantic repository of models available at the cloud. Besides, ASSIST-IoT also brings a large toolset of services that can increase the security, privacy, trustworthiness, and monitoring capabilities of the entire system. More information of the enablers that have been implemented can be seen in the project documentation.
The Smart Orchestrator offers us the capability to monitor our different Kubernetes clusters. But what does this mean? We can manage 3 groups of resources easily: clusters, repositories, and enablers. When referring to Kubernetes clusters, it's about the cloud and an associated edge. The tool allows us to add and remove them, as well as create a mesh so that they act as a single entity, enabling us to connect services located in different places as if they were in the same location. Additionally, there's the option to manage Helm chart repositories, where all project or external enablers are stored, with the ability to update them when a new chart is added. The instantiation of enablers offers 2 paths: doing it manually or through the scheduler, which selects the cluster based on certain policies for the instantiation of the enabler in question. Each of them has an associated network policy that only allows connections between the main interfaces of each enabler and connections between components of the same enabler, thus providing an extra layer of security. Modifications can be made to the values during instantiation to change enabler variables. In the pilot, there were different challenges: the need of scalability, the fleet management, and the dynamic ecosystem without static edge. So the IPs were dynamic. The smart solution for these environments involved using MQTT with the capability to instantiate enablers in groups of vehicles, for example, vehicles for the same model. Creation of instructions queues when cars are offline, and above all, scalability. Scalability is a key element for monitoring enablers in thousands of cars. The smart solution offers the creation of vehicle groups, vehicle creation, and enabler instantiation at any time with respective monitoring.
In our setup, we have access to several hundreds of measurement channels because we are interfacing the PCM, the control module, which is controlling the power gain of the vehicle in real time, so we can just get the measurements from the different sensors in the vehicle and also different calculated channels on demand. In addition to that, we have installed a set of advanced sensors, a cylinder pressure sensor, which is just measured in crank angle domain, or high fidelity emission sensors, which are able to provide a reference value for the detection of drift in the series sensor for emissions. The architecture we are using allows to integrate different vehicular systems using CAN bus or Ethernet or Wi-Fi, MQTT or Modbus RTU. For that, we have a compact Rio from National Instruments, which is able to integrate all CAN signals and digital and analog signals at high frequency. We also have a router which is providing the connectivity in the vehicle for 2G, 3G and 4G, and also GPS tracking. And finally, we have the edge device where we can deploy our software. In Pilot 3A, we have developed a range of enables capable of being dynamically installed and adjusted. These enables can be installed either to a group of vehicles or to a specific vehicle. Among them, one particular enable gathers files produced by measuring systems to process data, obtaining dynamics and emission metrics for trips. Furthermore, this enable forwards these metrics to the cloud through the router by several means and stores them in an internal database. Additionally, a different enable allows you to select which stored files you wish to recover from the edge for detailed analysis of selected trips. To receive the geolocation data from the trips and recover the files from the edge, they must have previously been accepted by the end user. For the case of fleet monitoring, what we want to address is the possibility of getting the instantaneous emission profile of each one of the vehicles in real time, and at the same time being able to get relevant metrics for the fleet as a whole and just for detecting the different outliers in the fleet.